Hey there, and welcome to the second YouTube channel I'll probably ever make in my life or video. I don't know what I'm doing, but anyways, I'm here to talk about RL circuits, right? So, an RL circuit just stands for a resistor and an inductor inside of a circuit. I'm going to draw one for us real quick. So, hopefully you know what this symbol is right here. If you don't know what it is, I don't know how you're passing the class, but this right here is a symbol for an inductor. What an inductor actually is, it's a spiral of metal inside the circuit, right? And it just kind of looks like a big coil that's placed inside of the circuit. So I'm going to go back and I'm going to talk a little bit about inductance real quick, because we have learned that magnetic fields are actually created by current. So with current, when current happens, is that it creates a magnetic field and magnetic field lines that will interact with objects around it, right? Pretty simple stuff. But what's actually crazy about this is, if you remember Lenz's law, the magnetic field that is created has a current of its own, but it's going in the opposite direction of whatever caused it to be made in the first place. So when we turn on this circuit, what actually happens is that the current coming through here is going to create a current in the opposite direction. So I'm going to draw a graph of what the current looks like when we actually turn on this circuit. So here I have time on the x-axis, I'll have amps in the y. This dotted line up top is what our current should be, or I naught, okay? What actually happens is at the very beginning, amps rises really fast, but then it kind of starts to level off, like a logarithmic function. And it is a logarithmic function. The actual equation that we use to describe inductance as a circuit is that current at a time after you have initiated the circuit equals the current naught, whatever it should be, with 1 minus e to the negative t over our time constant tau. So this equation should look familiar, and that's because we used the time constant tau idea before. In this case, tau will equal our resistance over L, inductance. And inductance is what measured in what's called henries, which is just a unit of inductance that represents how fast a material will create a current in the opposite direction when a current's going through it. But what's crazy is, as you can see, it's a logarithmic function. So what happens is current is going to increase really fast, but then it's never actually going to reach our I naught. It's because the magnetic change causes electrons to start, or current to start flowing in the opposite way of what it was originally doing. But then because it's not changing as much over time, it slowly starts to reach where it's supposed to be, right? So the same principle applies when we shut off the current as well. Because we create magnetic flux, current isn't actually going to just disappear. It's actually going to keep going this way because we're creating magnetic flux in the same direction the current was already going. And so here is what the graph of current versus time will look like as we're shutting it off. This line is where we originally were at. It's just going to fall really fast still, but then it's going to kind of level off again. And we'll still have some remaining current even after a couple seconds of shutting off the switch. So the equation that we represent that is I equals, it's going to be, I naught times E to the negative time over time constant tau. So just a reverse equation of this one, really. So yeah, it's kind of cool. But I am now going to make a quick demonstration of what this actually is, right? So we actually have inductors inside of our phones. Wireless charging uses magnetic flux to create current in our phones, and what I'm going to show was that obviously when I connect my iPhone to this charger, it starts charging, right? As expected. But here's what's actually kind of crazy. You can see that charging symbol up in the corner, right? As I remove my charging pad, it stays charging even when I'm away from it for just a second. Right? I'm going to show it one more time. Hopefully you can catch it, right? There you go. It's charging. It's still charging. I'm going to remove it. Still charging. Still going. Now it's off, right? And that is inductors in effect. We're still having current being created because the inductors in the circuit are assisting or aiding in the flow of current inside of our phone. So that's all. Enjoy.